All right, let's talk about AI performance. Today, we're going to pull back the curtain on what really drives latency and cost when you're running large language models at scale. And I'm willing to bet it's not what you think. Let's dive in. So, you're in the hot seat, right? You're planning a big AI deployment. Could be a brand new feature for your customers, or maybe something to make your internal teams way more efficient. Either way, you're at the starting block, trying to map out what you actually need.
And where does your mind go first? Of course, the hardware. The big questions immediately pop up. How many GPUs are we going to need? How much VRAM is enough? How many T-flops should we aim for? It feels like the most concrete, logical place to start.
But what if I told you that's kind of like picking out the tires before you've even designed the car? Because while those hardware specs are important, they're not the main story. In fact, focusing on them first is super misleading. This is what we call the GPU fallacy, the idea that just throwing bigger hardware at the problem will make it go faster. The real story? Oh, it's so much more interesting. To really get this, we've got to pop the hood. We need to follow a single prompt on its entire journey, from the moment a user hits send to the second a response starts appearing on their screen. And trust me, it's not a simple A to B trip. You know, most of us picture it like this. Your prompt goes in one side, hits the GPU, some magic happens, and the answer comes out the other side. Simple. But the reality? Oh man. It's this complex, multi-stage pipeline with more than 10 different steps. The gap between that myth and the reality is where all the performance gets lost. And here's a peek at that pipeline. See that? The actual GPU work is just one step. Step 5. Look at everything that has to happen before we even get there. Tokenization on the CPU, waiting in a queue, getting scheduled. The GPU part is just one piece of a much, much bigger puzzle. Everything else is where the sneaky little delays and costs are hiding. Okay, so let's start our investigation. We're going to look at the first two culprits that cause trouble way before your fancy, expensive GPU even wakes up. These are the CPU and memory traps. It all kicks off with something called tokenization. Sounds technical, but all it is chopping up your text into little pieces the model can actually read. And man, this is the very first invisible tax you pay on every single request. And here's the problem. Tokenization runs on the CPU, and it's often not very efficient. For a long prompt, it can easily add tens of milliseconds of delay. Think about that. Your request is already late to the party before the AI has even seen the invitation. And when you're under heavy load, this CPU bottleneck is often the very first thing that breaks. And this is the mistake so many teams make. I see it all the time. They'll spend weeks benchmarking GPUs down to the millisecond, but completely forget about the CPU path that's feeding them the data. This is why you can have GPUs running at 100% and still be failing to hit your performance targets. All right, next up is the KV cache. And if tokenization is the invisible tax, the KV cache, well, it's the monster hiding in the closet that just eats your VRAM for breakfast. It's basically a memory bank that stores the model's scratchpad, helping it generate new text faster. The thing you've got to understand is this cache just grows and grows and grows with every word the model generates. Pretty soon, it's taking up more memory than the actual model itself. And this, not the model size, is what really limits how many people can use your service at once. It's the #1 cause of those random, frustrating slowdowns. And that brings us to this huge illusion, right? The idea that, hey, the model fits in VRAM, so we're good to go. No, you're not. That is just the price of admission. The KV cache can and will demand way more memory, proving that a real production system needs so much more than just enough space for the model weights. So we've seen the issues with individual parts, but let's zoom out now, because the whole system is like a city grid during rush hour. It's just full of potential traffic jams, from the way you handle requests to the software you use to orchestrate everything. Take batching, for instance. Sure, cramming a bunch of requests together makes the GPU happy. It's way more efficient. But what about your user? For them, it's like being stuck in a long line at the checkout. They have to wait longer for that first word to appear. You're sacrificing their experience for your machine's convenience. And this is what we call an amplification trap. You have this tiny, little inefficiency in your system, seems like no big deal. But then it gets multiplied by thousands or millions of requests. And suddenly, that tiny little problem is your single biggest cost driver. And it doesn't stop there, right? You've got network hiccups causing jitter. You've got different parts of the system fighting over the same resources like CPU cores or memory bandwidth. And this is why benchmarks can be so deceiving. They're often run in a perfect little bubble that looks absolutely nothing like the chaotic reality of a live production environment.
So, what's controlling all of this chaos? The scheduling, the memory management, the batching? It all comes down to one thing: your inference runtime software. And believe me, this is not just some minor implementation detail. It might be the single most critical decision you make for your entire stack.
Just look at this. I mean, it's wild. You can have the exact same model on the exact same GPUs, but based on the runtime software you pick, you could be paying 3 times as much. The software you choose is a massive lever on both your performance and your wallet.
So, after all that, how are we actually supposed to think about planning for performance? Clearly, the old hardware-first way is broken. We need a totally new mental model, one that flips the whole process upside down.
And here it is. This is the real bottleneck stack. You don't start with GPUs. No way. You start with your users. What do their prompts look like? Then you model the CPU-bound tokenization. Then you model the VRAM-hungry KV cache and how it impacts concurrency. Then the system stuff. And only at the very, very end, at the bottom of the list, do you start talking about hardware specs like TFLOPS and VRAM.
So let's just reframe this and say it plain and simple. Scaling LLM inference isn't a model problem. It's not even really a GPU problem. What it is a classic, hairy, complex, distributed systems problem with all the tough challenges that come along with it.
And that's really the heart of it, isn't it? If your whole planning process just revolves around sizing up TFLOPS and VRAM, you're spending all your time, money, and energy optimizing what is, frankly, the least interesting and least impactful part of the entire system.
So I'll just leave you with this one question to think about for your own projects. Ask yourself, are you just optimizing your specs, or are you truly optimizing your system? Because trust me, the difference between those two approaches is everything.